Hello math fans, welcome to our next video on sequences. In the previous video we defined the notion of infinite sequence, that is a list of numbers, and talked about how to find limits of those sequences. In this video we're going to talk about a very important class of sequences, those that are monotone increasing or monotone decreasing. So a sequence a sub k with index k running from 1 to infinity is said to be monotone increasing if a1 less than or equal to a2 less than or equal to a3, etc. That is, each term is at least as big as the one that comes before it. Sometimes a sequence of this nature is called non-decreasing, but we'll take monotone increasing, non-decreasing to mean about the same things. Notice that the less than or equal to sign here says that it is possible that two consecutive terms are equal. A sequence b sub k with index k running from 1 to infinity is monotone decreasing, sometimes called non-increasing, if b1 greater than or equal to b2, etc. That is, each term is less than or equal to its predecessor. Let's look at an example. The harmonic sequence 1, 1/2, 1/3, etc., the sequence of reciprocals of the integers. This is a monotone decreasing or non-increasing sequence because, as it's easy to see, 1 is at least as big as 1/2, is greater than or equal to 1/3, greater than or equal to 1/4, etc. And for the generic terms out here, the kth and k plus first, it's clear that 1 over k is at least as big as 1 over k plus 1. A constant sequence, say the sequence that consists only of the number -3 repeated, -3, -3, -3, is both non-decreasing and non-increasing. Another example, let's take a look at the behavior of the sequence a sub k, defined by a sub k equals e to the k over k, with index k running from 1 to infinity. This sequence is not as obvious as the ones we looked at before. So we can always get a feel for what might be going on by calculating the first few terms, and we've done that here. We'll see that a1 starts off as e, which is about 2.72. a2 dips down a little, 1.85. Then a3 is larger again, 2.23. a4, 3.41, etc. Is this sequence non-decreasing, non-increasing? Neither. Well, let's analyze it, see what we can say here. So if we graph the sequence, so the graph we see here on, well, in fact, both of these graphs consists of the k running along the horizontal axis here. In the left, k runs from 1 to 7. In the right diagram, we've looked at more terms of the sequence. K runs from 1 to 20. And in the close-up view with 1 to 7 over here, we can see that the a1, as we saw, starts about there. a2 gets a little smaller. Then a3 gets bigger again. And then that trend seems to increase. And that's shown also here on the right one, although it's a little hard to, on the scale of things, to see what's happening for the small values. So it appears that this sequence decreases from a1 to a2, that is just at the start, and then increases from a2 onward. We can verify this using Calculus 1 tools. So some of these techniques we learned last semester can come in helpful. For real numbers, x bigger than 0, let's set f of x to e to the x over x squared. Note that for positive integer k, fk is e to the k over k squared, or ak. So this function, in a sense, defines the sequence. We're going to determine the intervals on which f is increasing and the intervals on which it is decreasing by examining the first derivative of f. So here's our calculation of the first derivative. We use the chain rule here. The derivative of the numerator, so e to the x prime times the denominator x squared, minus the numerator, e to the x, times the derivative of the denominator, x squared, divided by the square of the denominator. And after we do the work, which isn't too hard, this comes out to be e to the x times x minus 2 over x squared. Recall that e to the x is always positive. It doesn't matter what the x is. And in addition, note that at least when x is bigger than 0, the x cubed is also positive. So the algebraic sign of this derivative is going to depend only on the x minus 2 factor. Again, as long as x is bigger than 0, If x minus 2 is positive, the derivative will be positive. And if x minus 2 is negative, the derivative will be negative. So if x is between 0 and 2, then f prime of x is less than 0, and f decreases on this interval. This implies, for example, that f1 is bigger than f2, or a1 bigger than a2, as we already observed. If x is bigger than 2, then f prime is greater than 0, so f increases on this interval, and in particular, that leads to the other behavior we saw that seems like f2 less than f3, less than f4, etc., and that indicates the sequence is increasing once you once you hit the point k equals 2. So this sequence k runs from 1 to infinity, increases from k equals 2 on. Now, one of the nice things about increasing or non-decreasing sequences is that they cannot oscillate. The terms of a sequence like this can only stay the same or get larger as k gets larger. There's not going to be any dips in the sequence, it just continues to grow. Or you make a similar statement about decreasing sequences also. But the upshot is this: the non-oscillation of the increasing sequence implies a very useful result, and that's this, that if the AK is a non-decreasing or increasing sequence, then two things can happen. Either the sequence converges to a finite number, or it diverges to plus infinity. There's no other choices. So a monotone increasing sequence cannot diverge by oscillation. In a sense, it always converges if you allow going to infinity of type of convergence, that we usually call that divergence. So two choices: converging to a finite number or diverging to infinity. And this will prove very important in our following work, in our later work with infinite series. As an example, let's look at the sequence a sub n, defined by the square root of n squared plus 2n minus n as equaling a sub n. This is defined for n equals 1, 2, 3, 4, etc. So we want to take a look at the sequence a sub n, and we're going to show that it is increasing and bounded above. We're first going to show the sequence is increasing. This can be done by using algebra to rewrite the formula for a sub n as follows. So here's a sub n. There. We're going to multiply the top and the bottom by the so-called conjugate of the expression root n squared plus 2n plus n over root n squared plus 2n plus n. This is technique we have seen before in evaluating some limits. And when we do the algebra here, the difference of squares formula makes the numerator n squared plus 2n minus n squared, and the denominator just stays root n squared plus 2n plus n. Next, a little algebra. The n squareds cancel in the numerator, and if we multiply top and bottom by 1 over n, as we did here, thinking of 1 over n as, in a sense, the largest power of n that appears in this expression, the n squared appears under a square root, so we think of that roughly as n. And a little algebra again. We multiply the 1 over n into each numerator and denominator, and we find 2 in the top. The expression on the bottom is a little more complicated. You should work that out, make sure you understand the algebra. But once we clear things up under the radical, writing this as 1 plus 2 over n under that radical, we get the expression we see right here. And in this form, it's pretty easy to see that the sequence a sub n is non-decreasing. In particular, for any positive integer n, we can write a sub n here. If we replace the n by n plus 1, we get a sub n plus 1. And a little thought shows you that the denominator on the right is a little bit less than the denominator on the left, and dividing a number by a smaller denominator makes for a bigger fraction. So this inequality is verified, and that shows an is less than an plus 1. So therefore the sequence is increasing. Showing a sequence like this is bounded above often takes a little bit of insight. There's lots of techniques to do that. In this case, we can do the following. So again, let's write a sub n right here. And notice we can get a number bigger than a sub n just by adding this 1 under the radical. The nice thing about that is that makes the expression under the radical a perfect square, because the square root of n plus 1 squared is n plus 1. We get n plus 1 minus n, or 1. And so the upshot is that the a sub n's here are less than 1 for all n, and therefore the sequence a sub n, as we've seen, is bounded above. So it's bounded above by the number 1. So combine our work, we see the sequence a sub n, n was 1 to infinity, is both increasing and bounded above. Two very important concepts. And by that result we saw a little earlier, that means the sequence a sub n converges to a finite real number. It's a nice exercise, kind of reviewing some notions about limits. You might now try to find out what that limit is. So what do we want to remember from this video? Well, a very important definition. A sequence a sub n, when n running from 1 to infinity, is called monotone increasing or non-decreasing if the terms get larger as the index grows. Now, sometimes, as we saw in one example, it may turn out that a sequence decreases for the first couple terms, first 3, maybe 10 terms, but it might start increasing later on. We want to be sure we know how to recognize that behavior also. There's also the notion of a monotone decreasing or non-increasing sequence. The a sub n is monotone decreasing if a1 greater equal to a2 greater equal to 3, etc. In our work, we're going to deal far more with monotone increasing sequences, but everything we say about monotone increasing sequences has a version for monotone decreasing sequences. The other important notion, a sequence is bounded above if there is a finite real number, let's say a, such that a n less than or equal to a for all values of n. Again, this must be a finite number, not infinity, and if there is such a finite number, the sequence is said to be bounded above. Likewise, a sequence is bounded below if there is a finite real number, in this case we'll call it b for below, and we want all the a sub n's to be bigger than or equal to b. And then this important result we saw earlier, suppose a sub n n less than 1 to infinity is a sequence of real numbers. If the sequence is both monotone increasing and bounded above, then the sequence must converge to a finite real number. This will be a very important result for us when we move on to our study of infinite series. On the other hand, if the sequence of real numbers a sub n is monotone increasing and not bounded above, that means no matter what number you pick, you can find elements of the sequence bigger than that number. If the sequence is increasing and not bounded above, then the sequence must diverge to infinity. No other choice there. And again, we'll use this result quite often in our study of infinite series. And finally, just to keep in mind, although we won't use it very often, there is a similar result for monotone decreasing sequences. In this case, if a sequence is monotone decreasing and not bounded below, then it must diverge to minus infinity. So please keep these definitions in mind. We'll use them as early as the next section where we introduce infinite series and what it means for an infinite series to converge. Bye.